Hello my dear students, I hope you are all fine. We have studied before, as you know, section 1 and section 2 in chapter 11 about simple harmonic motion. Our topic today in section 3 about waves and what types of waves and properties of waves. So let's see at the beginning what's meant by wave. For example, if you throw a stone in the water like this, if you are throwing a stone in the water, it makes like disturbance in the water. So simply the motion of such a disturbance is called wave motion. So the wave is the motion of a disturbance. Simply the wave is the motion of a disturbance. And the particles of the water in such a case is called medium particles. Medium particles. So a medium is a physical environment through which a disturbance can travel. Again, the medium in a physical environment through which is a physical environment through which a disturbance can travel. So for example, in this photo or in this picture, the water is the medium for the ripple waves in a pond. But now the question is, do all waves need medium to travel through? Actually no. Some waves need medium to travel through and others don't need any medium to travel through because simply they can travel through vacuum or through space. So now we have different kind of waves, or we have two kind of waves in this point according to this point. Waves that require a medium to travel through, such as water waves and sound waves, which are called mechanical waves. Mechanical waves. So the waves that require a medium to travel through, such as water and sound waves, are called mechanical waves. While other waves which don't need any medium to travel through, such as visible light, radio waves, microwaves, X-rays, gamma rays, infrared, ultraviolet, all these waves are considered electromagnetic waves. So the electromagnetic waves don't require a medium to travel through, while mechanical waves require or need a medium to travel through. Let's see what else types of waves. If you catch a rope like this from one end and the other end is fixed at the wall, and just make a single pulse, just single traveling pulse, one pulse. So this kind of wave, simple wave, is called a pulse wave. A pulse wave. So the waves that consist of single traveling pulse is called a pulse wave. So what happens if you repeated it many times? Up and down, up and down, up and down the rope, or even your hand. By the way, you can do it, you can try it, your hand. For example, whenever the source of wave motion is a periodic motion, I mean repeatedly, you can do it many times, such as the motion of your hand moving up and down repeatedly. This motion, by the way, is called periodic motion. So with the wave in such a case is called periodic wave. Periodic wave. So again, whenever the source of waves motion is a periodic motion, not one single pulse, many ones, repeatedly, periodically, is called a periodic wave. So now we have a pulse wave, and another wave is called periodic wave. Periodic wave means repeatedly, or it is periodically repeated. That's why it's called periodic wave. Another wave is called sine wave. Sine wave, the wave whose source vibrates with simple harmonic motion. You remember the simple harmonic motion? The wave whose source vibrates, make a vibration with simple harmonic motion, is called a sine wave. So a sine wave is a special case of periodic wave. Actually, it is a special case of periodic wave, but in which the periodic motion is simple harmonic motion. Yeah, here is the motion is periodic motion, and in the sine wave it is simple harmonic motion. So I have studied a pulse wave, a periodic wave, and sine wave. Again, now there is a difference between pulse wave, if it is repeated many times, like in a kind of or in a shape of periodic motion, it will be called periodic wave. But if it is in a form of simple harmonic motion, it's called a sine wave. So the sine wave, for example, here, if this rope is fixed at this vibrating blade, okay, at this end, at the left side, and the wave actually is moving in the right side. What happens to the red point? Observe, notice well this red point. What happens to it if the vibrating plate stretch it or attract it to the left side? Again, the rope or the wave is moving in the right side, to the right side, to the right. But this vibrating plate trying to attract it to the left side. So this point is gonna move. This single point on the string move up and down with the rope until it passes on the equilibrium position. This dotted line is the equilibrium position. Here is at the highest point, and in the other example at the lowest point, again on the equilibrium position. So as a sine wave created by this vibrating blade travels to the right, it travels to the right, but actually the vibrating blade catches it or stretches it to the other side. A single point on the string vibrates up and down. This single point, the red one, vibrates up and down with the simple harmonic motion, means passing every time with the equilibrium position. Actually, this wave is called sine wave. Why? Why this wave is called sine wave? Because a graph of the trigonometric function y equals sine x. Y, if you want to get or calculate the y, the point on a y-axis, you can calculate it from the x by this equation. This trigonometric function y equals sine x produces this curve when plotted. When you plot the graph like this, you can calculate easily the y by or in terms of x. For example, here at x equal 1, if you want to calculate y, you simply can do sine 1 by the calculator. It will give you 0.8. So this is the y point, and you can easily plot a graph like this to get the sine wave. So again, sine wave is called by this name because a graph of trigonometric function y equals sine x produces this curve when plotted. So this curve or this shape is the shape or the form of the sine wave. Now let's see another type or another example. Again, you are catching a rope from this end, and the other end is fixed at the wall, and you're trying to move the rope up and down, up and down. So now I'm going to ask you a question. The direction of vibration is up and down or left and right? I mean, when you try to move it or vibrate it, the rope, you are going to move it up and down, so it will be vertical, in a vertical position or a vertical direction, while the wave, it moves in the horizontal direction towards the wall. So the two directions are perpendicular to each other. The two directions are perpendicular to each other. The direction of vibration you are doing and the direction of propagation or the motion of the wave itself. It will be horizontal while you are moving it vertical. So when the two directions are perpendicular to each other, this wave is called transverse wave. So the transverse wave is a wave whose particles vibrate perpendicularly. Vibrate perpendicularly to the direction of wave motion. The direction of wave motion is perpendicular to the direction of wave propagation, the direction of vibration. You are vibrating the wave up and down while the wave moving from left to right. So when the two directions are perpendicular to each other, such a wave is called a transverse wave. So can you see at the transverse wave, here is a transverse wave plotted on a graph. The highest points of this wave, the highest points away from the equilibrium position, by the way, the x-axis here is considered the equilibrium position because it moves up above the equilibrium position and back again down, up, down, and so on. So the highest points are called crests, while the lower points away from the equilibrium position are called troughs. So the transverse waves consist of group of crests and group of troughs. So the highest point above the equilibrium position is called the crest, while the lower point above the equilibrium position is called trough. What about the distance between two successive crests? For example, here is the first crest, and here is the second one. The distance between them, two successive crests, two following crests, is called wavelength. Wavelength. And the wavelength, by the way, is symbolized by this letter, this Greek letter, which is called lambda. Can you see it? Yes, this one is called lambda. Here is a Greek letter which is symbolized by the wavelength. Also, the distance between two successive troughs. Here is the first trough, here is the second one. The distance between them is called wavelength again, and symbolized by this letter which is called lambda. So the wavelength is the distance between two adjacent similar points of a wave. Adjacent similar points, two successive points of a wave, even if crests or troughs. So again, this wave is called transverse wave. The transverse wave is a wave that whose particles vibrate perpendicularly to the direction of the wave motion, and it consists of crests and troughs. Another kind of wave, for example, if you imagine that you are, this is a spring, okay, one end is fixed on the wall and the other end you catch it, but in this case, or in this time, you are gonna push it up, left and right. You are gonna push it in the direction of the wall. You are gonna push it, you are catching it from here and pushing in the direction of the wall. So now again the question is, the direction of vibration, vertical or horizontal? Horizontal, because in this time you are pushing it towards the wall, not up and down like the other time. And the direction of wave also at the same direction, parallel to it. So when the two directions are parallel to each other, when the direction of vibration parallel to the direction of propagation or of moving the wave, when the two directions are parallel to each other, this wave is called longitudinal wave. Is called longitudinal wave. So the longitudinal wave is the wave whose particles vibrate parallel to the direction of the direction the wave is traveling. When the two directions parallel to each other, not perpendicular like the other one, when the particles vibrate parallel to the direction of the wave, this wave is called longitudinal wave. And as you see, there are some regions which the spring is compressed, and other regions which is the spring is stretched. Here is compressed, here is stretching, and so on. So the longitudinal wave, by the way, on the spring at some instant time, and time is certain time, can be represented by a graph. We are going to show it how the graph is plotted. But the crests correspond to compressed regions. The compressed regions, like this one and this one, the compressed regions are called crests, while the troughs correspond to the stretched regions. So this one is called trough and this one is called trough. So the crest and trough here are different from those of the transverse wave. In the transverse wave, the crest is the upper point or the highest point away from the equilibrium position, and the trough was the lowest point away from the equilibrium position. But here, the crests corresponding to the compressed regions refers to the compressed regions, while the trough refers to or corresponds to the stretched regions. So we can define crest here, crest in the longitudinal wave, as a region for high density and pressure. High density and pressure. When the medium particles has high density and high pressure, we call it crest, but the trough are the regions of low density and pressure. The trough, this one, the stretched regions, are the regions of low density and pressure. So here is the crests and troughs in the transverse wave, the highest points away from the equilibrium position and the lowest points away from the equilibrium position in the transverse wave, while here the crests and troughs, x1, x3 are the crests, but x2 and x4 are the troughs, but here in the longitudinal wave. So here is the longitudinal wave and here is the transverse wave. The crests and troughs here are different from there, so you have to study it very well, the difference between transverse and longitudinal wave, because we are gonna solve some problems and we're gonna calculate the period, the amplitude, the frequency of such waves in our next session. See you inshallah. Goodbye.